Swayam Prabha. Digital India. Educated India.
Now, another way around this is what I will now talk about. It is what are called augmented Lagrangian methods. Now, the augmented Lagrangian method does something slightly different in the sense that it is not just looking for a minimization of a penalized problem. It is doing that, it is looking for the minimization of a penalized problem, but then it is not just doing this blindly. It is minimizing, it is looking at a certain type of penalized problem, it minimizes that penalized problem, but then the penalty associated with it is not going to be increased blindly, rather it is going to be tuned very carefully to the way we are getting solutions from this particular penalized problem. So, the effort is to eventually start mimicking these KKT conditions of the constrained optimization problem, and at the same time making sure that you get feasibility at a finite value of, even for finite values of the penalty parameter, right. So, let me give you, I will explain to you now what the augmented Lagrangian method is. Okay. So, recall what we know about what we had used as what was called the Lagrangian. The Lagrangian was a function of x and the Lagrange multipliers associated with it. So, I am going to look at a problem where so let me first write out the optimization problem. So, let us first look at a problem where with simply an equality with only an equality constraint. So, you are minimizing a function f subject to, say for simplicity, let's have only these equality constraints h j of x equal to 0 for j equals 1 to p, alright. Now, the Lagrangian is defined in this way. So, the Lagrangian was of x, and here if these are Lagrange multipliers theta. So, we define the Lagrangian as f plus summation theta j h j of x. The augmented Lagrangian is this particular quantity. The augmented Lagrangian is L of x comma theta, which is f of x plus, so this was summation from 1 to p. This is again summation from 1 to p. So, you have continue to have this particular thing theta j of x, plus you also include in this your quadratic penalty, and outside you can put a penalty parameter c. So, you have your quadratic penalty added on top of what's the usual Lagrangian. That is why this is called an augmented Lagrangian. So, you are augmenting the Lagrangian with this additional term, right. Now, what we would do is that the algorithm what it would do now is, you can notice that you do not have just the primal variable x, but you also have the dual variable or the Lagrange multiplier theta present here. So, it will continue to adjust x and theta at each step. So, and at the same time it will keep increasing Ck as well. So, actually to make the dependence on C explicit, let me write this as this given C, right. Okay. So, let us suppose we take the So, what it the whole idea is to start to have an is to adjust your x and theta in such a way that you start with an initial estimate of x, you start with an initial estimate of theta, and then as the iterations go along you start refining your estimates, and the goal is to get and is to refine them in such a direction that at the that eventually at convergence you would end up the minimizing this augmented Lagrangian would amount to the same as as minimizing the true Lagrangian and hence solving the KKT conditions, right. So, let me explain this. Okay. So, suppose we I have for sake of argument, suppose we have fixed, to motivate this, suppose we have fixed C at Ck. So, C equals, suppose I fix C equal to some Ck and I fix theta equal to some theta k, okay, at iteration k. And now, if we end up at iteration k, now with this suppose I minimize the augmented Lagrangian, right. So, then that would make that if I minimize the augmented Lagrangian to get a value x k, the x k is obtained. So, you minimize L of x comma with theta k given C k, right. You minimize this, and by minimizing this you get x k, right. Now, this would mean, sorry, the augmented Lagrangian. So, now this would mean that the gradient of the augmented Lagrangian with respect to x must be close to 0 or exactly 0 if you come to the exact solution. So, we would need that at x k, this theta k given C k should be approximately equal to 0. You calculate the gradient of the augmented Lagrangian, that turns out to be gradient of f plus summation j goes from 1 to p theta k j minus plus C k times h j of x k, the whole thing times gradient of h j evaluated at x k. Now, if you look at if you compare this with your KKT conditions, what you would want is that eventually this term here which is in the bracket, this should start resembling, we want that this should start resembling your optimal Lagrange multiplier. Okay. So, suppose this is, suppose theta j, suppose theta j star are the optimal Lagrange multipliers. Then in that case we would want this quantity, the one that I have put an underbrace below, that quantity should start resembling or start approaching theta j star, right. Now, I can rearrange this and write this in the following way. So, I write this as theta j star to be approximately equal to theta k j plus C k times h j of x k, or equivalently I say h j of x k is approximately equal to theta j star minus theta k j the whole divided by C k. Now, what this means is that if somehow I am able to get what the consequence of this little calculation is that it tells me that if I am somehow able to get this term here, the numerator to be close to 0. That means, if I have my Lagrange multiplier correctly figured out, that means if theta k is close to theta star, then even when C k is finite, I should still be able to make this get close, become feasible, make my Hj of x k close to 0. That means, that should approach feasibility even for finite values of C k. Recall, now this is exactly what we were trying to achieve when we introduced this non-differentiable penalty function. With the non-differentiable penalty function, we were able to do this by keeping we were able to use a finite value of the penalty parameter and yet get to the true solution and get to a feasible solution. Here is something similar is happening with a finite value, even with a finite value of the penalty parameter, we are able to get feasibility. Right? Now, this particular equation also gives us a hint on how exactly should one update the penalty the value of the theta k, right. So, what we did right now was we fixed a value of C k, we fixed a value of theta k, and we said let us minimize the augmented Lagrangian to get x k. And then what we are saying is, well, if we were nearly at the true solution, the way it should behave is that this should become equal to theta, this should become equal to the next optimal Lagrange multiplier. So, thinking from this, the way we update now our Lagrange multiplier. So, the Lagrange multiplier update Lagrange multiplier update is simply this, that I do theta k plus 1 j equals theta k j plus C k times H j of x k. I mean, does this for all j going from 1 to p. Right. So, this is basically the idea. So, the overall augmented Lagrangian method is then to do the following: you consider you consider a sequence of penalty parameters, consider C k that increases, an increasing sequence of penalty parameters, and so this I have taken this to go to infinity, but it is basically simply an increasing sequence. So, all right. So, you choose an increasing sequence of penalty parameters and start off with some value of theta 0, which is your initial guess about the Lagrange multiplier. Start off with some value of x 0, which is your initial guess about the primal solution, and then you iterate by doing the following: you minimize at each iteration you minimize this, overall x, and alongside, once you get the x, you also update theta k plus 1 as theta k for the jth constraint plus C k H j of x k, and you do this now in infinite loop. So, what one is doing effectively is one is doing by doing these two things. You are increasing the penalty for a parameter, and you are simultaneously adjusting the primal and the dual variables. So, this sort of a method is what is called a method which this sort of a method is what is an example of a primal dual method. Why is this a primal dual method? Because it's not just simply searching in the primal space, it is searching in the primal space and also at the same time using using what it's learned from the primal space to also inform or update the current guess about the dual variables. So, effectively it is if you think about it, it is operating in some sense simultaneously in the primal dual space, though priority is in some sense given to the primal space, and the dual space is treated almost as a parameter. So, one of the big lessons in optimization is that optimization is best seen through neither the primal space nor the dual space, but rather the jointly the primal dual space. When we did a study of optimization of duality in optimization, for example, our way of addressing that problem was through the cost constraint pairs, right, that could be attained by an optimization problem. So, that object was an object that lied jointly in the objective and the constraint space. So, analogous to that in the decision space is that is in the value space. So, in the decision space, the analogous thing to do is look at primal variables as well as simultaneously the dual variables. So, the augmented Lagrangian method is so effective because of this, because at its heart it is trying to play with both variables at once. So, it and is therefore attacking the problem in using all the levers available. Although it is not a full blown primal dual method, a full blown primal dual method is an example of a full blown primal dual method would be an interior point method, that is the method I will talk to you about next. But this method is sort of a stepping stone towards interior point methods, right. So, the main theorem that we have for this, for an augmented Lagrangian method, is that if essentially if so let x star be a local minimum of the constrained optimization problem, constrained optimization minimize f subject to hj of x equal to 0 for all j going from 1 to p. Suppose LICQ holds at x star and second order sufficient conditions are satisfied for theta j equal to some theta j star, then there exists a threshold, or let us say a finite threshold, C bar, such that for all C greater than equal to C bar, X star is a strict local minimizer of so it is a strict local minimizer of this augmented Lagrangian. Okay. So, from this theorem, so this is now not a complete theorem of convergence of the augmented Lagrangian method, that takes a little bit more to state. It is quite a mouthful to state that, but essentially from here what we are seeing is that if I fix the Lagrange multiplier at the optimal value, then it is enough for me to keep a finite value of the penalty parameter, and with that finite value of the penalty parameter, the solution of my original problem can also be obtained by minimizing the augmented Lagrangian function. Now, what one can do is build on this and then work with not the exact value of the Lagrange multiplier, but rather a value of the Lagrange multiplier that is approaching the optimal, and then from there one can conclude the convergence of the augmented Lagrangian method to a KKT point of the constrained optimization problem, right. Okay. So, this basically brings us to a close on this particular topic of augmented Lagrangian methods, but there is before I move to interior point methods, there is another type of method which I wanted to highlight and wanted to teach you about, which is what is called a cutting plane method. Now, this sort of method actually relies on convexity and makes very clever use of the convex analytic geometry of the problem. But it's not a very general method, but it is a very elegant method. Okay, so I would say that I thought I would just talk to you about it.